Okay, so let's start the second lecture. So so last time, at end of last time, we had these curvature evolution equations for Ricci flow. So, see, suppose I have a so on a okay. So then we have these curvature evolution equations. So just to remind you a bit. So if we write this in terms of in terms of orthonormal frame on the wedge second wedge product of tangent space. So then we have a d of dt square. So in particular, when the dimension is n, when dimension n equal to 3, so we know this operator here is just the determinant of times L inverse. Okay. So if since this is L this is simply is a curvature operator acting on this tangent space, I guess. Okay. So this if we in the n equal to 3 case, if we write if this is given by is diagonalized, so then this per psi of this, let's define this to be this here. It simply is this matrix, and guess I shouldn't cross the line, but now it's okay. So then this is the form. Because I write down a three-dimensional case because this is a particular case we are interested. I mean, so far certainly we haven't seen. The formula we derived works for any dimensions. So now let's see there's a corollary of this. By taking a trace of a curvature operator, you will get a scalar curvature. So the scalar curvature. So I guess I need to write bigger. So I look at R. So satisfies the following evolution equation. So it's a dr dt, okay, equal to Laplace of R plus twice of Ricci curvature of a square. Okay. So this you simply can taking a trace of this, you will get this equation. Scalar curvature is a scalar function. So here is a tensor. It's a tensor. Okay. So then we can get the following. And first, let me start with a simple application of maximum principle. So give you just a test of what we might get. So if we look at this, so define this R min T to be a minimum of a scalar curvature R x T. So that means a scalar curvature of a metric GT at the point X. Okay. So if we take this, then what we can get is from here, because at the minimum point, by a minimum point, Laplacian of that has to be a non-negative. So then what we know, this is dt is bigger or equal to twice of Ricci curvature. Okay. But scalar curvature is a trace of Ricci curvature. So use some standard inequality, you will get this is bigger or equal to 2 over n of a scalar curvature square. So let's see, this is so say this is R mean t. Okay. So of course this not necessarily a smooth function, but you have to understand this differentiation as a forward differences. Okay. So this then what we can do is we can look at so this if we set this st to be this function to be minus r mean of t. Suppose this is not 0. Okay. So let's just t of n and plus r mean. Okay. So say if okay, say if r mean 0 is not 0, so then we can at least consider this for it makes sense for when t is sufficiently small. So then what you can check then this inequality simply says s prime t is bigger to 0 whenever it's defined, and also you can check s0 is certainly 0 by definition. Okay, so that implies this so st is bigger to 0, so then you can just play around a bit, and you will see the following 3 conclusions. So first, so if r mean is 0 is non-negative, okay, so then what you can get is this r mean t is bigger or equal to r mean 0, and then the times 1 and minus 2t of n r 0. Okay. So of course, here in the proof, I assume the r mean 0 is not 0, but it's okay. And if r mean 0 is 0, this is automatically true because from this equation here, we already know this is so from equation from this simply from here, we know the r mean t is monotonic is long decreasing. So if this is 0, of course either this is always true. Okay, so if it's not 0, then we can simply apply the things argument here. So second, so if r mean 0 is negative, okay, so then what we conclude here is you can just simply play around this. So this t is bigger or equal to a minus of and 2t plus n. Okay. So you have again this the low bound of scalar curvature and is as you evolve along the Ricci flow. So this is give you a nice low bound and simple low bound. So this is of course just on the scalar curvature because its function is we can apply standard maximum principle. But now we also want to extend this to tensors, to a curvature operator itself. So then we need some generalization of this maximum principle to tensors. So here is some things we can have. So first, let me see recall things. So let's see recall some of these basic facts. Okay. So it can be easily proved. So say suppose I have a vector field. Okay. Suppose I have maybe I use say this is a vector space. Say suppose I have a Z, which is a closed subset, closed and convex. Convex. Okay. So let's say I have a psi here, which is a vector field. Defined on an open neighborhood U, say containing a Z. Okay, just containing a Z. So then we say following a standard thing, we say it's a psi. Let's say preserves of Z if for every point in the Z, this psi x is contained txz. So we have to be a little bit careful here because, of course, if x is in the interior point, this is nothing because certainly every vector is contained there. So this condition is basically on the boundary because in that case, so if I have, for example, I have a convex set and so if x, the condition is really on the boundary. So this is actually condition is on the boundary. Okay. So then the tangent space here means the tangent cone at this point. So for example, at a smooth point, of course, this is just half of space here. So that means psi pointing inward directions. But if you say I have a convex set, if it has a collar, then the tangent cone is, it's, if not smooth, then tangent cone is like this. So that means psi in these directions. Okay, psi x. Psi. So roughly speaking, so this is just this vector field on the boundary of Z points inward. Okay, points inward. So then the standard fact is following. So psi preserves Z in that sense if and only if any integral curve of psi which starts in a Z will stay in a Z. Okay. So if you have some integral curve in starting in this convex set, so it will never go out. Okay, it will never go out. So this is some standard fact. So in order to describe this maximum principle for tensor in the tensors, let's just try to make it globalized, make this definition globalized. So then I state theorem. The proof is basically, and maybe I shouldn't say. Let's first make a definition. So let the pi say I have a tensor bundle be a vector bundle. A vector bundle, okay, over. And the Z is a closed set. It's a closed. Okay, so we say so Z is convex. So that's so Z is convex if for any x in the M and Zx, the contain the fibers is convex. Okay, so it's a rather standard. So also you can say if a psi is a vector field, so this is one definition here. So Z is convex. Okay. So second, if a psi is a vector field, again on the neighborhood in a neighborhood of Z. Okay. So and it's a fiberwise. So it's a fiberwise vector field. So let's see. So that means along each fibers, when you restrict this vector field on each this subset, then this points is tangential to the fibers of this vector bundle. So then we say a psi preserve a Z if every every restriction psi x, which defined to be a psi restrict to a Zx, does. Okay. So now we can state the maximum principle. There are several versions of a maximum principle here. To save time, I just state the one version actually is a rather general form. It's quite a general form, and I'm not going to prove these things. So the proof is you just use the supporting functions because and various assumptions, conditions. Is convex set is defined in terms of supporting functions. So you apply the supporting function to these tensor equations, then you can reduce the standard maximum principle. Okay, so I rather just give you details on the applications. So here is the theorem. Okay, so it's a useful tool. So again, we have a manifold, and I have a vector bundle here, a tensor bundle here. So say so this is the tensor bundle. Okay, so it's particularly it's a vector bundle, and the Z is a closed. So Z this time now. Actually, I want this to be a. Okay, so this time I want Z to be also be more general. It contain the Z cross 0 time t. Okay, so be a closed set. Okay, and such that satisfy. Okay, first this Z restrict each time t. So Zt defined to be a Z restrict to this V cross T is convex. Okay, it's convex. So as we defined over there. So secondly, for each of these Zt is I just need to so and the Zt is also is invariant and parallel transport. Transport of transportation of GT. So with respect to the Vitavita connection of this metric at a given time. And also I want this, so suppose I have a vector field. So there's a vector field per psi. Okay, it's a fiberwise vector field, and preserves Z. Okay, so per psi again is a fiberwise vector field over there. Okay, just save time. So now I suppose I have a section, say a family of sections, say a T, say be a family of sections. So it's from M cross 0 T into your V. It's a family of sections, and satisfies a equation. So satisfies this d t plus, not plus, and the per psi. Okay, satisfy this. So then the conclusion is if per psi, if t of x0 is contained in x is contained z and 0. Okay. Then for all the x, it's then contained t. Okay. So I said I am not going to prove this. The proof is you try to use the supporting functions, apply to this, apply a support function of this convex set and to this tensor, and then try to using a maximum principle for scalar functions. So the parallel transport, this invariance and the parallel transport is used because basically you can if you pull in near given point, you are doing applying a maximum principle, you can pull back nearby the values of these at nearby points by parallel transport. Then they become like then this set become like constant set at that time. Okay, so I want to give an application of this. Okay, so maybe you can take a stare at that theorem for a few more minutes. So meanwhile, I clean up blackboards. So for example, you can look at what we have here. So since now we look at so now we do application. Basically, so basically we apply this equation to this the t. We take is just this curvature tensor, so which I did before, or it's just the curvature tensor here. Okay. So since the curvature tensor, curvature operator is a symmetric. So let's say so if we diagonalize this, see if say this is diagonalized, so it's just given by and if say alpha beta to be a t the g alpha delta alpha beta. So then if you apply to this operator, of course the square alpha beta is just simple computation. And also you apply to this. So by definition, this is given by this C alpha and delta and the C of beta, and I forgot the notation I used before, but anyway, gamma C. Maybe I wrote the other way around. So of T of delta gamma, T of okay. So then this will become, if you diagonalize, it will become this. You see this become diagonalized, so this will become C alpha and gamma C, okay, square, and then this become T gamma and C. Okay. So in particular, you can easily see from here, this is if curvature operator is positive, curvature operator is positive. If a curvature operator is positive, so namely all these eigenvalues, all these so then of course this is still non-negative because this is square, and then this is also non-negative. So this this is also big equal to 0, and in particular, so consequently, this if I define psi, as we said before, big equal to 0. Okay. So when the curvature operator is positive, then you have this. You have this. So of course you can check that even more directly when it's 3-dimensional, because you write down every you have a very explicit form for this. So once we okay, so in a curvature operator, so it's preserved by and the Ricci flow. Okay, and the proof is very simple, since I will give you a proof of a pinching result. So this case, what you can define is so this time you can take a z is actually independent of a t. You just define z as all the symmetrical tensors. So maybe I write down a bit. So you take this the tensor here, just this bundle, and symmetrical product of this bundle. Okay, and the t is okay. So z is just all this a in the v. So this is a symmetrical operator. So you just say the smallest eigenvalue of this is big equal to 0. So this is just the least eigenvalue of A. And clearly this is a convex set, and it easily you can check that properties. Okay. So last thing you check is this vector field is preserve this z, because whenever curvature operator is non-negative, this is non-negative. So any integral curve will stay in this set. In this set, as long as it starts in the set. Okay. So then you apply it. Okay. So this curvature operator is preserved. In the case of n equal to 3, this curvature operator is the same as a sectional curvature. So in a dimension equal to 3, It just means the sectional curvature is preserved. Sectional curvature is preserved. Which is not necessarily true in the high dimensions. Okay. So another corollary, which I'm not going to prove, is if n equal to 3, then the Ricci positive is preserved. Again, this is the property of three-dimensional case. Okay. So in order to do that, you just this time you take z to be a. So this time this is a. So then this is so you write say a has say suppose a is diagonalized. And so then this condition simply says mu, and this still convex set. Okay. So of course, so maybe I put it this way. It's more okay. So then you apply the maximum principle. So you can only do this when dimension 3, because in the high dimensions, again, the positivity of Ricci curvature may not be preserved at the flow. Okay, so this the corresponding set in the high dimension is not as good as this one. And there are more. So in these lectures, we are mainly talking about three-dimensional case. So there are some for last 2 years, and also particularly recently, there are some progress on the high-dimensional cases. So, for example, this Balmer and Wilkin, proved the extension of this maximum principle, and they were able to prove for this along the Ricci flow, the curvature operator. If you start with a metric, the Ricci flow, the curvature operator is positive, then it will, of course, it will stay positive. But then they prove that it's after appropriate scaling, it converges to a space form. And same thing applies to a curvature pinching case, quarter pinching case. That was done by recently by Ricci and Simon Brandl. Okay. And if you want to talk more about that, we can discuss later. But I will not do anything on that in this class. So now I want to do a key theorem in the 3 dimensions. So that's Hamilton and Ivy pinching estimate. So it says as follows. So M, so this is for 3 manifold, a closed 3 manifold. Okay. Then we consider the Ricci flow. So we have a Ricci flow. As we started. So I make the following assumption. So that let's first make a definition. So this mu of xt is the least eigenvalue of a curvature operator. Now this time it's a 3 by 3 symmetric matrix. It's a okay. So, and I assume this. So this is just you can simply achieve this by scaling the metric appropriately. Assume this x0 initially is always bigger to -1. So I normalize the curvature so that the initial value is always bigger to -1. This is not a very serious constraint because you can always scale the metric so that this is true. Okay, but it makes a statement more. It's make it convenient to state the result. So then we set x, capital X. Of course, this is also depends on t and the position. This is maximum of minus v and 0. So I just take the absolute value of this mu if it's negative. Okay, otherwise I just make it 0. So then we have the following things. The first one is already have it. The scalar curvature is bigger equal to always bigger to minus 6 1 plus t for t again. Okay. So this is already we proved. So this you just go back check, plug in the right dimension n, you will come out with this. So I already did it. So secondly, that's more crucial. For all xt for which capital Xt is positive. Okay, so that's the point where the curvature is not positive. It actually has some negative eigenvalues. So then what we have is the scalar curvature of xt. So this is like twice of a trace of this curvature operator. Okay, so this is like twice of a trace as a 3 by 3 matrix here. So this is bigger equal to twice of xt and the log of xt and plus log of 1 minus t. So before I prove this, let me say so what the consequences it might have. So this imply by just some simple linear algebra, because we are just talking about giving a symmetric 3 by 3 symmetric matrix here. The trace of this matrix is bigger equal to a smallest absolute value of smallest eigenvalue. So that will imply, you will check this implies there is a function phi. Okay, so this function may depend on initial metric, such that this function. So let's see, this function defined from 0 infinity to r. Okay, you can make it even non-negative, but it's not that. So such and the c0 such that this as a matrix. Okay, so this is bigger equal to phi r times r and minus c0. I also need these things. Sorry, with a limit phi t equal to 0 as t goes to infinity. Maybe I should put r to r here. Okay. So maybe I put it this way. So as t goes to infinity, this is goes to 0, and also C0 positive, such that this is 2. Okay. So we call this. So then, if this is true, then we call this this curvature is phi C0 pinched toward positive. Okay, so we call this towards things of curvature. So it does not imply a curvature is positive. Of course, we cannot have that, because if we take any metric to start with, of course, you might have a negative curvature. But if you go along the flow on the 3 manifolds, this tells you as a matrix, and this how do I say? Maybe I should I reverse a little bit. So sorry, I take it back a little bit. So from here, basically it says the choice against the smallest eigenvalue, the smallest negative eigenvalue, is actually the ratio is getting bigger. Okay, getting bigger. So in particular, this time this side is less equal to some constant multiple of largest eigenvalue. So this says the largest positive eigenvalue compared to smallest eigenvalue is much bigger. It's much bigger. So in particular, that will imply if your curvature become very big, that has to be the case if a Ricci flow develops singularities. Then this actually scalar curve become positive because this is a much bigger number here. Okay. So the scalar curve become positive. Then here you will tell you actually the modulo this constant here. When the scalar curve become very positive, this is actually almost like a non-negative curvature operator. Okay. So that's very important because once eventually we want to come to classify all the possible models for singularities, and then all these models will have a non-negative sectional curvature. That makes things possible to do. Okay, make classification possible. So any questions? Otherwise, I go to prove this theorem. So it's very nice proof, and it's not arguments are rather elementary, but it's very nice. So now let me prove a theorem. Maybe I start. I better still do here. Okay. Proof for theorem. Okay. So let's of course we still try to apply a maximum principle in this form. So again this is the same as before. Just and it's a curvature operator. Okay. So now let me try to let me introduce this z here. Okay. So first we observed one thing. So we look at this functional equation here. Okay, plus so for fixed t, we try to solve this functional equation for x. So there are two solutions. So there are has two solutions. Okay. The first is, of course, is clear, is this solution, which we are. So 1 plus t 1. Okay. You can check directly. This is the solution. And second, I have another solution I call Ct, which is not explicit, but this is strictly bigger than, sorry, I should, yeah. T. Okay. So I will call this side. So I give a name for these things. So let me call this side, give a name. So this is called ft of x. Okay. So now let me draw a picture and to indicate. So. Okay, so now we set S, okay, S and xt just to be a trace of curvature. Of course, the scale curvature is twice of the S. Okay, and also I set this xt already defined. It's a minus of it's defined before. Okay. So this is yeah. Okay. So okay. So we define Z1 to be all these. The matrix inside of this tensor bundle, and SA trace of this is 3 by 3 matrix. It's bigger than bigger equal to minus t. Okay. So this is one set, and the other set is Z. Okay, and this is okay, S of A bigger equal to FT of X A. Okay, so XA is defined this way. Maybe I should define this A and this. How do I say? So this is maybe I put this way. A to be this to be A, and A. This is the smallest eigenvalue. I'm sorry. Okay, and this is the least eigenvalue of this matrix A. Okay, and so if x again, I guess if x of A bigger equal to Ct. Okay, Ct. So this all both sets depends on T. Depends on T here. Okay. So actually we are defining a family of sets which parameterized by t. So small ft is giving over there, and so the z is t. Just z, I guess. So now we have a first, and you check a few things. The first thing you check, let me give a, let me say first, it's easy to check. It's clearly this is a closed set because we are using a continuous functions here. So for each x and m and the t, this z xt, which contained in the is a closed and convex. Okay. And also, it's clearly it's invariant and the parallel transport because because parallel transport will not change these properties. Okay. So it's a convex because basically what you are doing here is you can think this is maybe I just indicate. If you look at this map, A is a notation for this. Maybe I just goes to S A and X A. Okay. Then this is maybe I draw the picture here. So this is X, this is S. Okay. So we have two functions. So one is so this is given by S equal to ft of x. Okay. And so then I have one line. Have this second line here. So maybe I just put it here. Okay. So this maybe I draw a little bit more than I needed. So I think I draw more than I needed. Sorry. So anyway, it's sorry. Okay. So this is the intersection c x c t. Okay. And this line is given by s equal to 3 of 1 plus t, this line here. Okay. So there's another solution here which is given by 1. So this is given by 1 plus t here. So the region we are considering is basically this. So maybe I use the so and this is a convex set. Okay. So this is your CT. Okay. So your Z is just the ZT is just the pre-image of CT. And clearly this is a convex set, and you can use this fact to check the pre-image is convex set in the spatial metrics. Okay. So you can also say it's parallel, invariant and parallel transport, because I said before this is these conditions are invariant there. So second, so gram 2 is you can check this is this curvature operator. So namely, this curvature operator at x0 is contained in the z x0. Okay, for all x. So why is that? It's easy to check. That's basically use the first property we already proved. It's so this is the same as the this S0 as this x0 of x0 is contained in the C. Yeah. Okay. So let me maybe slow down a little bit. Maybe I slow down a little bit. So let's say a proof. So since I by initial assumption, so this is bigger equal to minus 1. So then this must bigger equal to minus 3. Okay. So this is less equal to 1. So that's, you can easily check this must be here. Okay, must be here. So if this is okay, let me see. So if do I need to do anything more? It seems to be clear. Okay. So since this point is when x equal to 1, so it should be on this side, and on the other hand, s is above that. Okay, so that's so. Okay, so then actually are done. So what I stated before is right. So it's so then that implies clamp 2. Okay, that's all because it's pre-image of this will be in the Z. Okay. So the first two are easy. So last one is involves some series, some key computation here. So I want to prove. So basically, last I want to say this vector field preserves Z. Okay, so that's preserve convex set of Z. So in order to prove that, what we need to check let gamma t be an integral curve of psi. So you want to say if it preserves this. Okay, the gamma 0, I assume is contained the x0. Okay, maybe I take how do I say? So take an integral curve. Maybe I put it in the general form. It's defined on a. So let's say t is between t0 and t1. Okay, so then we said we want to preserve its we need to preserve this is always stay in the Z here. Yes? Per se is a vector field. It's in this time it's just this per psi is so because I talk about curvature operator here, so this is T. Okay. Yeah. So ST they define to be S applied to this T. S applied to this curvature at so this is gamma T. So, okay, gamma is an integral curve, so it's a family of 3 by 3 symmetric matrices here, and similarly you have XT. Okay. Okay. So now the computation tells us this computation shows a d of s dt. Okay, and using this equation here, and remember this is when the a is diagonalized. So anyway, so how do I say? Okay, so this is lambda square in terms of eigenvalues. So this is mu square plus okay, and okay, and you can write this as So then those are eigenvalues of this corresponding matrix here. So this is bigger equal to 2 over 3 s squared over 3. Okay. By elementary inequality. So and in particular, this is bigger equal to. That's all I needed. So this is the ordinary differential equation. So if we check if an initial value is right, then we will have a corresponding property along the time. So initially, since gamma t0 is inside of z x t0, okay. So here we just fixed x and t0. So I should say so here in this argument, because we just check this is we check this property pointwisely, so we can fix so here we fix the x a point. So since we have this, that means s t0 is bigger equal to minus 3 or 1 plus t0 by definition. Okay, because z is the intersection of two sets. So then using this ODE here, so that implies. Okay. So the first is easy to check. We best. I'm sorry. Maybe I turned the ring off because I need the time. I cannot receive a phone call here, but turn off the ring. So Okay. So now since it's more involved is checking this condition here. So namely this psi preserve this set, this subset. So let me do some computations here. So now let's assume. So now we assume. Okay. So we assume this is this xt is positive. Because that if xt is not positive, of course, there's nothing to check because this is because definition of this set here. Okay. So to check the second condition, we can assume this is this xt is positive. So then what we have is we compute the dxt. Okay. So let me make some convention here. Let's assume this also assume that say arrange eigenvalue so that this is bigger equal to mu and bigger equal to mu. So this is minus x. Okay. So we will so define this to be minus y just for convenience. So this is same as minus d mu dt, which is equal to minus mu square plus minus lambda mu. So this is minus x square and plus lambda capital Y. Okay. So on the other hand, we can rewrite that equation. Maybe I just write down result now. It's elementary. So this you can rewrite that in terms of okay. So and the lambda y and lambda square, sorry, plus xy minus lambda x plus y. I mean it's straightforward. Okay. So I'm putting this together. I put x times ds dt minus s time. I mean, of course, this is basically you have to do this because kind of inequality you want to prove. Okay. So if I check this, so this is x cubed plus I. So where the I is capital I is these things. Okay, and y minus x and lambda. Okay. So I have another claim. I say I is always bigger to 0. Maybe I leave this. It's rather easy to check, and maybe I leave that out. Okay. So let's first say this is always bigger to 0. So then then what we have here, because this is bigger to 0, so you can drop this term. So this is simply says this x ds dt minus s plus x dx dt is bigger equal to x squared, capital X cube, x cube. So if we said so that's the equivalent form that if we take w to be s over x minus log x. So you see, so this is inequality. This is a major term in the inequality we want to prove. So then if we write this, so this simply says dw dt. If you look at here, so dw dt equal to x. So this is same as this. So we have this, and x is okay. So now let's just try to prove it and prove that this claim 3 by using this last equation here. So okay. So suppose this is not true. Say suppose this there is a suppose there is a t0 prime contain the t0, t1, such that this s t prime 0 and x t0 prime, or maybe I just put the t here. Okay, and such that this is contained the boundary of CT, boundary of CT. Okay, so then there are two cases. So one case, the case 1 is the S T prime is equal to ST1 plus T prime. That means it's on this on this portion of a boundary. So this I have this gamma T0 here, and then it's say a gamma T prime. So that means that it's on this boundary point. So if that is the case, then and also xt prime is less than ct prime. Okay, so that's that portion of boundary. So then what we get is the following. Let me see. So okay. So we already know the S is so this is actually easy case because we already know this is so this condition will be preserved for a while. But on the other hand, we already know the S from here that this ST is always bigger or equal to 3 over that. So that means this is not cannot be go out of boundary here. Okay, so we really want to see this is after that is go out of boundary. Okay, so this is probably the last point in this set.
I guess when you picture the boundaries, it's a little bit lower, right?
Oh yeah, sure. Okay, thanks. So I need the boundary. Okay, but since this nearby this point, this we are still less than that. So, but on the other hand, S is always bigger to this above this line, so this cannot go out. Okay. So this case is we don't need to worry about that. Okay. So this case I don't need to worry about that. So not possible. Okay. So gamma T stays in a C T for T close to T prime. Okay. So case 2, okay. So case 2 is I want to go to other side of boundary, so X T prime should be bigger or equal to C T prime. Okay. And then the S, so then the S T prime is on the boundary, so this has to be F T prime of X T prime. But this time I know this is bigger than 1 plus t prime, okay? Because the choice of this point here. Okay? So then this will be true. So I will say, so then this implies this xt will be bigger than 1 plus t for t close to t prime, okay, for t prime, because this is strict inequality there. So that will imply, we back to this equation here, that implies dw dt is strictly bigger than 1 over 1 plus t. So if I integrate this, I will get this, if I integrate this, I will get this is, okay. So if I integrate this, I will get w, also I know this, the t prime is the same. Okay, maybe I write down to give me some time to get used. So this is a w over w times x. So maybe let me just slow down a little bit. So w plus log 1 plus t and minus 3 and x. Okay, t prime, sorry. So then this simply tells us, this simply, because x is positive, so I'm sorry, that's just a moment. So this is not w, so I should put minus here. Okay, so then this will be a w. Okay, this will be a w. Okay. This will be a w. And this also is a minus. Sorry. Okay, minus. Okay. So that's what I have. So x is positive here. So only thing I need to check this is positive. Okay. So then this will go back to your region here. So however, if I integrate this, that's I simply get w minus this simply says dt of w of maybe x, and let's put this way, st minus ft of x over x. Okay, that's exactly this function here. This is positive for t close to t prime, close t prime. So then we are done. So I know this is an increasing function, but on the other hand, at t prime, this is 0. 0 here, okay? Because this side is 0. Sorry. So this is 0. Okay. So that implies this is always positive. So st is always strictly bigger than ft for t for t close that. So then this is not possible either, because this will stay. So both cases will imply, and so that both will imply. So I get this and st, and so gamma will stay. So this proves this last claim. And this one can be checked a very easy way. You just divide. Maybe I just say a few words, and so to check that particular claim, you can just divide into two cases. For example, one case is if you assume, say, y less equal to 0. If y less equal to 0, then I know that y less equal to 0, that implies mu is positive, so lambda is positive. So then this term is certainly is non-negative, and this term is non-negative. So I guess, and then this is non-positive, and this is non-positive. So if y is less equal to 0, this is true. So then you check y is positive, but in that case you can rewrite this as the following. So this you can rewrite this as so this check y less equal to 0 case trivially, and then second case you can rewrite this as y minus x minus y, and the lambda square minus lambda y. So this you can check when the y is positive. So y is positive and this is non-negative. Okay. So both cases check. So using these two different expressions, you can check both cases. So once I have these, then you can apply maximum principle. You get so apply maximum principle to get okay. So this is a proof of this theorem. This theorem here. So in the next few minutes, I want to. I don't have time to go too much into that, but I want to say a few words about the strong maximum principle and give you some splitting theorems. Maybe I only have time to state it. And okay, so I want to say, okay, next application of so-called strong maximum principle. So rather to stay there, which I just give a state corollary now. So the best, what is strong maximum principle? Basically, it says if you have an equation of say a Ricci equation on a okay, suppose you have a Ricci equation. Suppose this is on the U cross say 0t. Okay, say 0t here. Okay, and suppose and h x 0 is bigger to 0, and of course on the boundary of this is bigger to 0. Okay. So then the maximum principle says the following: then we know, of course, the h is always non-negative by maximum principle. But strong maximum principle says that actually you can get more things on that. So if x 0, so maybe I put it this way, is positive for some x in a U, then the strong maximum principle says this h x s dot t is positive for t positive. Okay. So not only you can prove this is non-negative, actually you can prove this is you can make it strictly positive. So this is a simple property of Ricci equations. Okay. So if we apply this to this geometric situation, Ricci flow case, we can have a theorem like this. So I will state, I don't know if I have time for two theorems, but at least I state this one. So I suppose a U of GT. Okay. So say a T0 is a Ricci flow. It's a three-dimensional Ricci flow. It's actually, this is true for any dimensions. So it's a Ricci flow. Okay. So with a non-negative sectional curvature. Okay. Maybe I just make it three-dimensional. Otherwise. So with non-negative sectional curvature, okay. So and with U with U connected, so I need to say this is connected, otherwise, okay, U is connected, of course. Okay. So, okay. So then what? So if say also assume this is positive, otherwise there's nothing to do. So if a scalar curvature is P is 0 for some P, okay, in the U, sorry. Then what I want to say is this is flat. GT is flat. So that means the curvature come identically to 0. Okay. So the proof is simple. Let's see. So okay, so the proof is it's as follows. Since if first we observe if we prove by contradiction, say if not flat, if false, so then we can say the Ricci curvature and the curvature of since this is positive, it's non-negative. So we may assume this. Scalar curvature of x0 is positive somewhere. Okay. Okay. So then what you can do is you can find the function, find h with find h such that solving this equation here, such that star holds, and also h and at the boundary say it's identical to 0, and Rx 0, R dot this is bigger than H dot 0. And also this is H is not identical, positive somewhere. Okay, positive somewhere. So we can find this. So then the strong maximum principle says that H x t is strictly positive for any t positive. Any t positive. So now you go back to this equation. At the beginning I said this is dr dt equal to r and plus twice of Ricci curvature square. So that implies this dr minus h dt equal to Laplacian and bigger to 0. You can drop last term. Okay. So now this function, difference function by choice of h here is always non-negative on the boundary and initially. Okay. So then the standard maximum principle says that this is so here is a strong maximum principle. So now standard maximum principle says this is R is always bigger to H. So in particular, so R P T is positive. So that's a contradiction. So the contradiction comes because you assumed this. Because you assume this is not flat. It's not flat. So that implies GT is flat. Flat. Okay. So you can go further. I guess my time is up, so I stop here. So you can also apply the maximum principle to tensors, which will take a little bit of time to state. So when you apply to tensors, then you can conclude the following things. Namely, if you go along the Ricci flow, if a curvature operator either becomes strictly positive, or if it still keeps some 0 directions, that will force your manifold split, because this 0 direction will be preserved. And then you play around in this property of curvatures, you will be able to prove the underlying manifold after you evolve along the flow a little bit will split. Will split. So then it forces your manifold split into low dimensional ones, and that is helpful, okay, useful. So I think I stop here. When I need that, I will probably bring that up again. Thank you.